What is up, you guys? So in this one, we're going to be talking about the secant method, and we're going to see how really similar it is. Actually, it approximates the Newton's method. By the end of the lecture, we're going to see a MATLAB implementation and see how secant works on multiple functions. So without further ado, let's get started. Okay, so I probably repeated that 1,000 times, but the goal is always the same. That is, all we're trying to do is find the root or roots of the following function, f of x equal to 0. Could be any function, linear, nonlinear. And for conditions so that it works, the secant method follows almost the same conditions as the Newton's method. That is, the derivative should exist at each and every point. It shouldn't be 0 so that the thing doesn't blow up. Because, you know, Newton's method, here's a small recap on Newton's method. We said that Newton updates as follows. So xn plus 1 is xn minus a step where this local approximation applies. We talked about this in the previous lecture on Newton's method. To see a detailed, intuitive explanation on why Newton's method looks like this, I'll leave the link to the previous lecture in the description below. So why am I writing Newton's method here, even though the lecture is about secant's method? Well, it's because secant's method, the way I see it, the way it is that it further approximates Newton's method by replacing the derivative over here with something that doesn't depend on the derivative. And I find that quite amazing. Why am I saying this? It's because when you implement this on a computer, imagine each and every time you have a function, you want to input it to the computer, you want to run Newton's method, it has to iterate over that function. Well, guess what? Newton's method requires full knowledge of the derivative. Secant's method, on the other hand, uses a finite difference approximation. So, in case you don't know, and you've probably seen this 1,000 times in calculus or in high school, that any function f prime of, I don't know, a, is actually computed as a limit. So, you take the limit as h goes to 0 of the following term, f of a plus h minus f of a over ah, right? Well, the finite difference method tells you, oh, okay, since we're going to be a bit realistic over here, we're going to work with discrete values, we can omit this limit and say that h is small, okay? So we can go ahead and say f prime of a actually is an approximation of this guy given a very small h, right? Makes sense because this guy, I mean, you could approximate it given that h is small, no? Okay. Well, we have f prime xn. Let's see how this applies. Let's see if we can make use of this finite difference method. Okay, we have this approximation. Well, let's say let a be our xn, right? Because at the end of the day, we care about this guy over here. Let's see what we get. So f prime of xn is nothing other than f of xn plus h minus f of xn over h, right? Well, here comes the trick that tells us, okay, well, since h is small, this applies for small h, remember, for very small h. Okay, and positive h. Well, since h is very small, then in principle, we can pick it whatever we want, given that it's small. Well, a reasonable value over here would be to pick h to be the difference between the next iteration point and the current iteration point, xn plus 1 minus xn. Okay, well, why do we care? Well, because we need this guy to be a function of values that we have in hand at this current iteration, and that's very important. You don't want to be adapting h or fixing h at every given iteration. It doesn't make sense. And this is also, you know, in finite difference method, well, you could see this as a forward iterative approximation. So if we embed this, what we get is, now that this is also means that xn is xn plus h is xn plus 1, right? So xn plus h is xn plus 1, so we get f of xn plus 1 minus f of xn over h, which is the difference. So xn plus 1 minus xn. Right, so now we have a finite difference approximation of our derivative. And the thing to keep in mind here is that this doesn't depend on the explicit form of the derivative. So this is an approximation. All this is an approximation. So we can replace this guy in Newton's method and see what we get. So again, Newton was given by the expression xn plus 1 is xn minus fxn over f prime of xn. Well, everything remains the same, but now we're going to replace this approximation. So this guy comes and sits here. What we get is simply fxn plus 1 minus fxn over xn plus 1 minus xn. Okay, well, we could get this denominator up, right? Using x over 1 over b is bx. We get xn plus 1 is xn minus fxn into xn plus 1 minus xn over, right, fxn plus 1 minus fxn. Okay, well, this is one form of what we have in hand. Another form, you can write this as, if you factor this guy, if you take a common denominator, I mean, what you get is the following. So xn plus 1 is xn into f of xn plus 1 minus f of xn minus f of xn into xn plus 1 minus xn over what we have in the denominator, f of xn plus 1 minus f of xn. Now, why did I write this as such? Because there's some terms that cancel. What are they? Well, let's expand the numerator to get xn into fxn plus 1. Well, I see it from here. I just want to expand to convince you, and that's all. If you're wondering, here you've got an xn multiplied by fxn, right, with a minus. And here you've got the same term, fxn and xn, but minus times minus is a plus, and so they cancel. Well, let's expand. So minus fxn into xn plus 1 plus xn f of xn, right, over the same term. Okay, so you've got this guy and this guy that cancel. So you might also find the following expression for secant. That is xn into fxn plus 1 minus xn plus 1 times f of xn over f xn plus 1 minus fxn. And this form is what is known today as secant's method. And it's actually lovely. If you look at it, it looks nice. What I mean by nice? Well, you've got xn fxn plus 1 over here, and then you've got the function applied on xn over here. So once on xn plus 1 and once on xn. And in the denominator, you've got the same thing, but without the x's. And the striking fact over here, the thing that I find mind-blowing, is that this method, even though one might think, oh, it came after Newton as an approximation, but no, this method actually existed 3,000 years almost before Newton's method. So yeah, pretty mind-blowing. And actually this has another derivation in case you're wondering, but I gave you a nice way to see it as an approximation of Newton's method. This could actually also be proven by taking slopes at each iteration, applying a linear interpolation, and so on till you reach the n+1th point. Sort of like an induction type of proof. or derivation. But yeah, this is one nice way of seeing how Secant's method relates to other methods such as Newton. Okay, so that's it for the explanation around Secant's method. And now let's go to MATLAB and see how to get this thing done. Right, so I'm on MATLAB and I'm in the same folder as that used when implementing bisection and Newton. And I've got a main, and if you recall, if I run this main, I will be plotting the different iterations of different functions, right? For bisection, Newton, and the true value, right? And one thing to mention is that for the particular f3 of x function, we saw that Newton converges to another root, which is okay. So we're going to use the same main function and build on top of it, as we did with Newton and bisection, build a function to call here to check how secant converges, if it does. Okay, so for that I'm going to create a new, let's say function, call it secant. Let's open secant. And okay, let me maximize over here. So we're going to input f, x, and the number of iterations that I want to execute. The output, as with the bisection and Newton, will be the next iteration, x, and the error based on the error function. So it's the function evaluated at the current iteration value of x, that is xn. So the input over here would be my f, that is the input function, right? My x, so current iteration value, call it xn. This is relative. If you call it xn minus 1, then the output is x, right? And if you call this xn, then the output is xn plus 1. So this is really a relative notation. Depends what you mean by... yeah, this could be xn minus 3, then the output is xn minus 2, if you know what I mean. Okay, and one last thing is the number of iterations. All right, number of iterations. Okay, and for the output, I'm going to input x, which is next iteration value. Or actually, you know what? Let's do this quite generic. Let's input the first value x0. Okay, so this guy is x 0, why not? And the output is a vector x containing all the iterations, containing all iteration values. That is, x would be x0, x1, x2, all the way down till x n iteration, like this. Okay, good. Likewise, I'll copy paste this. Error will be defined the same way. So it's the error vector f of x containing the values fx is 0. You can define it as such, really. You can define it as such. And you can define it as the difference between each two consecutive iterations, right? In other references, you might find this. So right here, you could find that you have, I don't know, x1 minus x0. So this is the relative error. Not relative, because relative you have to divide it by something, x0 or x1. But the difference, let's put it that way, the difference between any two iterative points. Up till xn iter minus xn iter minus 1, right? We're going to work with the second one, so I'll omit the first one. Okay, right, so now, well, unlike Newton, that only depends on the previous point in terms of xn, right? So if we go back to the Newton's implementation, which I had here, as you can see, xk depends on xk minus 1, right? Of course, it depends on the function and its derivative, but in terms of x, it depends on xk minus 1. So it has a memory, but in terms of memory, this goes back one step. Well, secant does it twice, so it has a memory of 2 points. So it depends on, if we go back to what we have here, it depends on, so xn plus 1 depends on xn plus 1, and oh, I have a notation mistake over here. This guy should be xn plus 2, xn plus 2. So all those are xn plus 2, okay? Let's correct this. So instead of 1, 1, 1, 1, what else? 1, this guy should be a 2. So xn plus 2, xn plus 2, xn plus 2. My bad. You see, I'm not going to just, copy paste from a certain reference or something. No, I'm showing you let's put it that way, a realistic approach of dealing with numerical analysis, approximations, applied mathematics, and getting simulations done on a computer to see how the algorithm works. I could have just copy pasted this from a reference, yes, but I'm just deriving it in front of you to see how you can build intuition, how you can connect the dots between different methods. Over here, yes, I did a mistake, and I'm not ashamed to, cut that part out of the video. Instead, what part of my teachings on YouTube is to show you how to, pinpoint mistakes that you did based off of, let's say, when you go to a computer, you want to type the algorithm and see how it works. You can start, going back to what you have on paper, checking if it's right or wrong, if it makes sense, if you did a certain mistake or not, and seeing, you get my point. So part of really working with algorithms and iterative methods and numerical analysis is not only to, just grab an algorithm from out there and, test it on a computer. It works. Okay, it works. And that's the end of the day. No, it's really to have a feeling of each and every term, how it's going to behave with each iteration. And that's what I'm trying to show you in this course. Otherwise, I would have, there's many interesting courses on the web, such as those by MIT or Stanford, or really other courses that are really informative. Yes, what I feel that I am giving as an extra, let's put it that way, because all this is classical. Secant is classical, bisection is classical. Yes, you can go ahead and check any other tutorial on the web. I agree. But I am showing you, on top of that, how to deal with mistakes that you might get done due to a typo. So yes, here, for example, is one instance where we easily pinpointed our mistake. Because if this guy was an xn plus 1, right, then it doesn't work, because you've got an xn plus 1 here, you've got an xn plus 1. So back to what I was saying, the next point, xn plus 2, depends not only on xn plus 1, but also on xn. So going back here, if I were to implement a loop going, let's say, from the second iteration to the last one, or actually from the third one, because x1 is the input, right, is the initial point. x2, which is, if we use the formula over here, would be x0, which doesn't exist. So we can, say that x0 is 0, right? So this guy is a 0. Okay, this is one way to deal with stuff. And right here, it's fx. It's fx1 minus f of 0 times x1. This is the numerator. Now, the denominator would be f of x1 minus f of 0, right? This is the exception for the first 2 points, but then it's really the same. So I'll copy paste this right here, and instead I have n plus, you can do this, but here you have to start with 0, right? Or you can do this, and here you do n, and then you express the others in terms of xn minus 1 and xn minus 2. So whichever you prefer. Let's do this. Actually, it's this, right? It's this. Okay, and over here, plus 2. Here you've got an n plus 1. Likewise here and here. And the 0 is xn, xn as such. This guy is xn and this guy is xn. Okay. Okay, and now the error Oh, we forgot to do error 1. So error 1, as we said over here, the definition, is the absolute difference between x of 1 and x of 2. Likewise, over here, for any iteration n, right, so n plus 1 now, not plus 2, because this guy, the error vector, is one length smaller than x. Imagine we have 2 points. Well, here we have only 1 point. Imagine we have 3 points. Well, here we have only 2 points. So this guy is 1 dimension less, and it consists of, if we want to see some similarities from here, I can copy paste this here. Well, my 1 is now an n plus 1, so this guy definitely should be an n plus 1, and this guy should be an n plus 2. Okay? Well, that's it. This is how secant is. Let's test it really quick over here. Let's do f of at x as such, or let's do x squared. And there's a fast way of testing. Let's start with point 1 and do 20 iterations. As you can see, we converge directly to 0 and then not a number. Why not a number? Because the denominator here will be 0. Once you have 0, then 0, and you evaluate x squared, you have to stop when the denominator is 0. Let's do that. So we can do over here if, and then else. So let's evaluate this guy first, right? Let's call that guy denominator, okay? Denominator. And if denominator equals 0, so this guy will sit here, we can output a message saying early termination, because this loop is expected to run n iteration amount of times, minus 1 or 2, right? But it didn't. And by the way, this guy here should be, look, here we did 21, right? So this guy should be a minus 1. See, I'm not trying to copy paste stuff. I'm trying to let you see how to check stuff, how to think by yourself. And this is very important. This is even more important to the content I'm showing. This is even more important than secant method. This is even more important than Newton's method. Even more important than any method you might know. It's how to think by yourself. Okay, so if the denominator is 0, early termination, or even more, you might find in some references that, on computers don't like 0. Keep that in mind. Computers do not like 0. So for computers, 0 means something really small. So for that, you might find a certain tolerance. So you might define a tolerance over here saying 1e minus 10. Let's say 0.10 is 1. And this would be our 0. So in absolute value, if this guy is smaller than a certain predefined tolerance, sometimes referred to as computer precision, okay, we stop. Else continue. And don't forget to break. Okay? So if I adapt my code as such, right? If I adapt it as such, and I run this again, I stop at the third iteration. There you go. Let's try it with another function. Let's do x minus 1 squared. And this time, start at 5. Let's see what we get. This is the error function. And here is our beautiful iteration converging to 1, which is the root. If I were to plot this, there you go. The root of x minus 1 squared is indeed 1. You have a drop over here, and it converges at 1. Okay? So our secant is working. Good. So now let's embed it or integrate it into our main function. So let me copy paste the function signature over here, right down here. So if this code looks bizarre or weird to you, I encourage you to check both my previous lectures, Newton and bisection, because it is thanks to both those functions we have built this main function. Okay, so I'm just going to, this function is doing nothing. It's just defining 4 functions just for testing. their derivatives, because Newton requires their derivatives over here. We've got MATLAB's routine, this fsolve function, just to check, for sake of checking if we're converging towards the proper root. And then over here, we run bisection 4 times each at its own function, Newton 4 times each at its own function. And now we're going to do the same thing with secant. x1, x0 was defined as 0, the starting point, so I'll just leave it as such. And right here, just to stay consistent with notation, I'm going to call this one x underscore 1 underscore secant. Likewise, error underscore 1 underscore secant. I'll copy paste this guy three more times for x2, x3, and x4. I might be going really quick here because there's nothing really fancy to be done. I'm not going to show you how I type them, right? And one last thing that I would like to add over here. Yeah, we're done. Now we need to plot. There you go. So over here, I'll plot x1 secant in a different color. Let's say in black squares, and modify the legend so that it properly indexes Secant's method. I'll copy paste the legend 3 more times here, here, and here, and I'll copy paste this plotting call over here, and over here, and let's run. Well, we have that. We terminate really quick. Here there was one iteration. Let's check the values actually. Let's check x4 secant. We cannot see what's going on because I have a main function here. So let me do a CLC and clear all and run this. Okay, let's check x4. Oh, we have not a number. Why? Because if we go back here, we didn't check this value over here. We have to check this one as well. So if this one is 0, also we have to stop. So let's do a bigger if else. So this is x1. Let's compute the denominator again. This is the first denominator, okay? The tolerance, let's place it here. And as we did down here, if this denominator is less than a certain tolerance, we're going to stop, else we'll continue. And we'll display the same thing. But we don't need a break over here. Okay? So again, what are we doing? This denominator, we're also testing, right? We're also testing. And then this guy will sit here, okay? So we're also testing this denominator. We should test this one. We tested all the others except the first one, which also should be tested. So that's what we did right here, okay? So run main again. We have an error saying the error was not assigned. Which means that this function did not reach this point. Okay, so for that, let's initialize the error to something empty. Okay, run again. Early termination for the 4 functions. Wow, we have early termination for the 4 functions, and as you can see, this guy didn't actually converge. If we take a look at x1 secant, just 0, which is not correct or not sufficiently close. So for that, let's try to tweak a bit the starting point. So let's do an x0 plus 1. And there you go. You can actually see that now we're talking. Now it's starting to converge. So the starting point of any algorithm or any iterative function is really important. You move it a bit and test. This is actually called perturbation analysis. You perturb your starting point and see how your algorithm behaves. This is a bit outside the scope of this lecture, but it's nice to have it in the background if you're subconscious. Know that it exists, know that actually there's some theorems around initializations of numerical methods. I won't be talking about particularly in this lecture, but I will definitely have lectures in the future for this concept. Okay, so now we see convergence. Now let's see this guy, same problem. Let's shift it by 1 and see what we get. And there you go. There you go. So now you see convergence. Okay. Let's see over here, same problem. How coincidental. Likewise, we add 1. Yes, we do start to see convergence, right? Yep, it's converging towards the green line, which is the root. And the last one as well. Well, the root is 1 over here. Let's push it to, I don't know, 5. And there you go. 5 is really far, huh? That's a far initial guess. And even though it converges. So 0 is not, for those functions, was not a good initialization point. Let's try something really large for this function. Let's try 50 instead of 5. You can see early termination for all functions except this one. There you go, 50. And there you go, convergence. Okay? So it's really nice to test with starting points to check convergence and these kind of stuff. Okay, so let's call this one a lecture. We're done explaining secant, its connections, so how we connect the dots between secant, Newton, and bisection. And one last thing is we saw how to get the job done on MATLAB. We saw how to implement secant and tackle edge cases. So for example, when the denominator is 0. So thanks for watching. If you found this lecture beneficial, please leave a like on the video, subscribe to the channel. We're actually really close to 100,000 subscribers, and I couldn't thank you enough. It really means a lot to me. It really means a lot to my journey here on YouTube. I've taken a commitment with myself to continue spreading knowledge based on you guys, your requests. Even though there's a join membership to my channel with additional perks where you will have early access to courses, lecture notes, and codes, I am trying my very best to, especially in this course, to have an article for each, or let's put it that way, a lecture note for each lecture. For example, for this one, I will have lecture notes with the link down in the description section below, with detailed explanation on what I just did, so that you have a reference on what went around in this lecture, and most importantly, the MATLAB code. So I am leaving the MATLAB code as well in those articles. This requires a lot of time from my side and a lot of effort, but if only one person is benefiting, that means a lot to me. And I really want to make this small difference, even though it's minor. So thanks for watching. If you found this lecture beneficial, leave a like on the video, subscribe to the channel, share it with other colleagues, and let me know what you think down in the comment section below. I'll see you in the next one.